So the first application of vectors thing that we're going to look at is the intersection of lines. And we'll do this in 2 dimensions and in 3 dimensions. So in 2 dimensions, there's 3 possibilities when you have 2 lines. They could be parallel. Like in this situation, they'll never intersect. They could also be, okay, well, I'll go through. You know if 2 lines are parallel if their slopes are the same. So if you set up a system of equations and solve it, you're going to find out that all your variables disappear. So we'll look at what that looks like. But one thing that you can do, as we see in this first example, is if you want to show that 2 lines are parallel, they have to be going in the same direction. Does that make sense? So in this case, are these 2 lines parallel? Well, what are the direction vectors? The direction of the one is 3, 2. The direction of the other one is 6, 4. Can you find a value of k so that they're equal? And in this case, if k is equal to 2, then you'd have 6, 4 equals 6, 4. And that means that they're going exactly in the same direction. Because the one that's 3, 2 says it's going over 3 and then up 2. And the one that's 6, 4 says it's going over 6 and up 4. And if you think about that slope or that vector, that's exactly the same. One is just twice as long as the other one. So those 2 lines would be parallel because they go in the same direction. I'm going to come back to this question and show you what it looks like when you set up your systems of equations to solve after we've done some of these other questions, like this one. 2 lines could cross. And if they cross, they intersect at a single point. So when you're trying to find out where they intersect at that single point, you're going to set up a systems of equations and solve it. And once you solve it, you can find out that intersection point. So what does that look like if we have vector equations? Well, we'll write out our parametric equations. For the first one, x would equal -3 plus t, and y would equal 5 plus 2t. In our second equation, x would equal 4 plus 3s, and y would equal 3 minus 2s. If they intersect, there must be a value for t and s that works out to the same point. So what we can do is we can use these equations, the blue and the green ones, to say that if the x coordinates are the same, then -3 plus t would equal 4 plus 3s. And if the y coordinates are the same, then 5 plus 2t would equal 3 minus 2s. So that's just equating the x's and the y's. And you end up with a system of 2 equations with 2 unknowns. And by now, we've learned a ton of different strategies for solving that. We could go back to our strategies we learned in grade 10 and grade 11, either substitution and elimination, to solve this. You could rearrange these equations and use matrices to solve it. So we've got a bunch of different options. Personal favorite of mine is elimination. So what I'm going to do is I'm going to choose to eliminate one of my variables. I take a look at my t and my s, and I ask myself which one looks the easiest to eliminate, and I think it's easiest to eliminate t. I'm going to take this entire first equation and multiply it by a -2. I'll rewrite that over here. That would give me 6 minus 2t equals negative 8 minus 6s. And then I'm going to rewrite my second equation. 5 plus 2t equals 3 minus 2s. What I wanted to do is I wanted to get the coefficients of one of my variables the same. And I've done that with my t's now. They're the same, but one is positive and one is negative. So now if I add these together, I'm going to get 11 plus 0 equals 5 minus 8s. Wait a second. Oh, negative 5, right? There we go. Add 5 to both sides, you get 16 equals negative 8s. So s is negative 2. Once you find s, you can plug that value back into either one of your equations and find out what t is. So if I would use this equation here, 5 plus 2t has to equal 3 minus 2s, and s is negative 2. Then I would get 3 plus 4 minus 5 is 2, and t is equal to 1. Once you've found both s and t, you can choose either your first equation or your second equation to find that point of intersection. So when t is 1 and I plug that in, I get negative 2 comma 7. When s is negative 2 and I plug that in, I'm going to get negative 2 comma 7. So I got that by putting in a 1 for here and then figuring out what my x-coordinate would be when I add those vectors and figuring out what my y-coordinate would be. Or I could put in negative 2 for that s and figure out what my x-coordinate would be. And the fact that they're the same means that they are intersecting at that point. So was it 2 negative 7 or negative 2 7? Thank you. Now the thing that happens most often when you solve equations is you get two equations that are concurrent, that intersect. So as a general strategy, you will often start with this. You will start by getting your parametric equations and setting up your system of equations. The thing that comes up is, well, what would have happened in that previous one if they just said, right, this previous example that we looked at and it said, show that they're parallel. If this question's instructions said instead, do they intersect or are they parallel? You would probably start by trying to find the point of intersection. So you don't have to write this down. If you want, you can look at this later on the video. If you had set this up, this parallel one, trying to find the intersection points. So here's my parametric equations for my first ones in blue. Here's my parametric equations for my second ones. And when I equate them, I'd have 1 plus 3t equals 2 plus 6s. And 2 plus 2t equals 3 plus 4s. And trying to solve this with a system of, or elimination, what I decided to do is multiply the first equation by 2, the second equation by negative 3, that would get over here on the left my values, my coefficients in front of t to be 6 and negative 6. So when I go to eliminate, though, my s's also got eliminated. And I get an expression like 0 equal to 1. What does that tell us? Well, 0 equals to 1 is never true. So this is the method to find a point of intersection. You set up your system of equations and you solve. If your answer is something that is never true, that means that those lines never intersect. And the only way lines can never intersect is if they're parallel. What I've also done here is showed if you would rearrange it and write it as a matrix equation, and you tried to find the inverse of this matrix equation, you'd get 1 divided by 0. Also something that's not possible. So when trying to find these things, and with a method that you use comes up with something that says this is not possible to do, well, the only way that that happens if their two lines are parallel and they never intersect. Because these are techniques to find that point of intersection. The third type of thing that can happen is two lines could be parallel but be exactly the same line. In other words, they're on top of each other and they intersect an infinite amount of times. So what would happen here is when you set up your system of equations to solve them, you get an answer that's always true. So if you get parallel lines and you get an answer that's never true, that means they're parallel and don't intersect. If you get parallel lines and when you try to solve them, you get something that's always true, like I said here, 15 is equal to 15. That's always true. Then you know that those lines are parallel and they intersect an infinite amount of times. In other words, they're coincident. So one thing to look for as sort of a helper along the way, can you see that these two lines are parallel just by looking at them? That you've got a direction vector of 3, 2 and a direction vector of 6, 4. You can almost think of those like fractions, because if I have a direction vector of 3, 2, my slope is 2 over 3. Rise over run, right? And the rise is your y, which is 2, and your run is your x, which is the 3. So it's kind of a flip of our slope. And if I think of this one, well, my slope is 4 over 6, but if you had a slope of 4 over 6, you'd just say, oh, I could reduce that to 2 over 3. So we already know that these two lines are parallel. We're going to show that they're exactly the same. If we were setting up our systems of equations to solve this, our first equation would be 1 plus 3t for the x-coordinate, and the y-coordinate would be 2 plus 2t. Second equation would be 7 plus x-coordinate would be 7 plus 6s, and the y-coordinate would be 6 plus 4s. Putting these two together, 1 plus 3t would equal 7 plus 6s, and 2 plus 2t would equal 6 plus 4s. If I wanted to cancel out a variable, I would, looking at my variables, they both aren't numbers that you could just multiply one equation by if you choose to get rid of the t's or you chose to get rid of the s's. So then I make a decision, okay, I'm going to try to get rid of the t's. If I multiply the first equation by 2, that'll give me a 6t. And if I multiply the second equation by a negative 3, that'll give me negative 6t. So writing that out, I'm going to get 2 plus 6t equals 14 plus 12s, and negative 6 minus 6t equals negative 18 minus 12s. And when you add these together, you get negative 4 plus 0 equals negative 4 plus 0. Or negative 4 is equal to negative 4, which is something that is always true. So since we got something that's always true, we know that these lines are coincident. So that's one way of showing that two lines are coincident. If you get a statement that's always true, you'll know that they're exactly the same line. The other thing you could do in a situation like this is you could show that the point 76, once you know that they're parallel, you could show that the point 76 is on the first line. And if two lines are parallel and they share the same point, then they have to be the same line. Okay? So one way to say, show I know that they're parallel, and then figure out that when t is equal to 2, (7, 6), can you see if I plug in 2, that I'd get the point 7, 6? 7, 6 is on that first line, R1, as well. So if it's on the first line, and that point is on the second line, and they're parallel, that would mean that they have to be the same line. So that's another way of showing it. But what I like about showing the system of equations is if you're using that as your go-to technique for finding a point of intersection, any one of these three situations could happen. You could find that point of intersection. But if everything cancels out, all your variables cancel out, you're either going to get a statement that's true all the time, like this, then you know that they're the same line, or you're going to get a statement that's not true ever, like 5 equals 12, then you're going to know that those two lines had to be parallel. Now in 3 dimensions, there's another possibility. So 3 dimensions has the same thing. It has, you could have two lines that intersect at one point. You could have two lines that are parallel that never intersect. You could have two lines that are parallel and are exactly the same line in 3 dimensions. But you could also have two lines that aren't parallel that don't intersect. So like an example I have here is 2 airplanes are flying. They're not flying parallel, but they don't crash, which is a good thing, right? If we lived in a 2-dimensional world, we'd have a lot of trouble with airplanes because they'd be crashing all the time. But in 3 dimensions, you could have one plane going this way and one plane going this way, and they wouldn't intersect. So I'm going to get you to try this one. 3, 8 is the point of intersection. So depending on how you eliminated, I set up my system of equation. I decided to eliminate this variable lambda, introducing new Greek letters for you, and found that t was equal to -5. Then I found lambda was equal to 4, plugged that in, and I got the point 3, 8. Ready to try the next one? I can go back, yep. So set up your parametric equations. You might have wanted to rewrite these as the vector equations to begin with. Forgot my little arrows over top of my vectors. There we go. Then when I equated those two equations, I decided it would be easiest to multiply the second set by 2 to cancel s. My t's were canceled as well, but I got 11 is equal to 11, which is always true. So I know that they're the same line, that they are coincident. When you write it as a vector equation line like we did here in the top right, can you see that those direction vectors are parallel? We have 2, -1, and -6, 3. If you think of that as a fraction, do they reduce to the same thing? -2/1 and -6/3? Yes. So we're given a hint that these are either going to be parallel lines that never intersect or coincident lines. So here's a three-dimensional one to try. So if you set up your parametric equations based on what we had to begin with, right there, you've got your x, y, and z coordinates for both of your equations, and then putting them together gives you 3 equations. 2 plus t equals 3 plus 2s is the first equation, and so on. We get 3 different equations. Now, we only have 2 variables, s and t, that we need to solve for. So if you have 2 variables that you're solving for, you only need 2 equations to do that. So what I did is I used equation 2 and 3 right here to solve for s and to solve for t. The reason I chose 2 and 3 is because I thought, well, t is already by itself, so it would be super easy to use substitution in this case. So we've been using elimination for a lot of things so far, but in this one I said it's going to be easy to use substitution. So I substituted t is equal to -1 minus s into equation 2. And from there I was able to solve that s has to equal 1. And when s is equal to 1, if I plug that back into equation 3, I get t is equal to -2. So what you can do is when using equation 2 and 3, once you've found one of the variables, s is equal to 1, you could plug that value of s equals 1 back into either equation 2 or equation 3, because those are the 2 equations that you're using. Once you've done that, you get a value, s is 1, t is -2. What we have to do, and this is something that's different for 3 dimensions, because in 2 dimensions, once you get your 2 answers, you're done, because there's only 2 points to find. But in 3 dimensions, you have to check if those values of s equals 1 and t equals -2 also work for that other equation. And when I plug in -2 for t and I plug in 1 for s, I don't get something that's the same. If I did get something that's the same, then I could find a point of intersection. But since I didn't get something that's the same, these lines are skew. They're not parallel, but they never intersect.